All right, so now we're going to talk about nodal analysis by inspection. Okay, so here's a circuit. We've kind of looked at this circuit before, but I'm gonna rederive the equation, rederive the expression, and then we're going to show that there's an interesting pattern that emerges, and you can leverage that pattern to make your calculations very simple. It's called nodal analysis by inspection. Okay, so we're going to do a nodal equation at V1. All right, so this is, we get an I1 coming in, an I2 going out. So this is I1 minus I2 plus a 0 minus V1, that's the current going through this, over R1, plus a V2 minus V1, that's the current going through this guy, over R2 is all equal to 0. I'm going to rewrite this now in terms of V1. So what I'm going to do is I'm going to move these terms over to the other side. Or another way you could think about it is, I'm going to multiply everything by -1, like so, times -1, and then move this over to the other side, okay? But, so we're going to flip the sign and then move that stuff over to the other side. All right, so what we're going to get is, we're going to get, this is equal to an I1 minus I2 over here. And then over here, attached to V1, we're going to have, you'll notice that you have a 1 over R1 here and a 1 over R2 adding up. So this is going to be 1 over R1 plus 1 over R2 times V1 minus, because remember we're flipping the sign on this, so there's a minus V2 1 over R2 times V2. Let me give myself a little more room. Minus 1 over R2 times 1 over R2 times V2 is all equal to I1 minus I2. Okay, that's equation 1 in this form. Let's do another nodal equation at node 2. Nodal at V2. Okay, so we get I2 coming in. So you have an I2 coming in plus the current from node 1. So this is going to be a V1 minus V2. We're doing far minus near here, right? Over R2 plus the current coming up through R3. So that's a 0 minus V3, minus V2 over R3 is all equal to 0. Okay, so let me put this, again, I'm going to multiply by -1 and move the other terms over to the other side. So we're going to get an I2 over here. And since I'm writing it that way, I'm going to flip the sign on the V1 and V2 terms. So notice that we get a V1 over R2 over here. So this is a minus 1 over R2 times V1. And then on V2, you'll notice that we have V2 over R2 and V2 over R3, right? So we're going to get a plus 1 over R2 plus 1 over R3 times V2. And all of that is equal to I2. Okay, and that's our equation 2. Right? I'm going to put this into matrix form now. Okay, so let's put this into matrix form. So the node voltages are V1 and V2. And let's look at equation 1. Equation 1 says on V1 there's a 1 over R1 plus 1 over R2 coefficient. And on V2, there's a negative 1 over R2 term. And all of that is equal to the difference between I1 and I2. Isn't that interesting? It's all equal to the currents, the sum of the currents in and out of the junction. Let's take a look at the second equation. So the second equation, we've got a minus 1 over R2 here. And then we've got a 1 over R2 plus 1 over R3 term here. And all of that is equal to I2. And we notice that that is the only current source entering node 2. Huh. I'm seeing a bit of a pattern here. This looks like over here, this looks like the sum of the currents into the node, right? I1 is going in, I2 is going out. That's interesting. This one here, it looks kind of similar to this one here down the diagonal, doesn't it? Huh. 1 over R1 plus 1 over R2, we could actually write this as G1 plus G2, couldn't we? Notice that that is accounting for the resistive path connected into node 1. In fact, all the resistive paths connected into node 1, and that one's on the diagonal. If you look at the value here, this is G2 plus G3. Isn't that interesting? That's the resistance, all the sum of the conductances connected to node 2, isn't it? Huh. We're seeing a pattern here. Let's then also take a look at what's happening on the non-diagonals. Here's a minus 1 over R2. Huh, that's a negative G2. Isn't that interesting? That's row 1, column 2. So that's between the node voltage V1 and the node voltage V2, there's a resistive path with resistance R2, or in other words, conductance G2, and we put it negative there. You'll notice the same thing. There's a negative, here's row 2 and column 1. That's, again, it's between node voltages 1 and 2. And the resistive path, again, that's a negative G2. Huh. So it looks like we could populate this matrix without even doing any nodal equations. So what I'm actually going to propose is that you don't even need to do this by nodal, but if you do nodal analysis by inspection, you can completely skip the nodal analysis setup if you trust the process of that this works. I'll take off my X marks there, so we are leaving the derivations on there, but that in fact is true. Nodal analysis by inspection, the general form is that along the diagonal in the coefficient matrix, I'll do it with the same colors I was doing on the last slide. Along the diagonal on the coefficients matrix, you put the sum of the conductances into that node. So when we say G sub I, remember that this is the row and this is the column. Okay? Like row 1, column 1, right? This would be row 2, column 2, and so on. So down the diagonal, when the ith values are the same, you put in the values of the sum of the conductances, every conductive path that's connecting to that node. Now on the non-diagonals, that is this G sub ij, okay, that's a random ith row and a jth column. You put in the negative of the conductance of the path between the two nodes. So if it's the first row and the second column, like I've got pointed there, it's the negative of the conductance of the path between nodes 1 and 2. If it's the first row and the third column, then it's the negative of the conductance between nodes 1 and 3. And if there's no conductance between them, i.e. there's no path between those nodes, then the conductance is just 0.